Hello.
What up?
Ooh, 9.
Learning targets.
Nope, sorry, 9.
So last video, we had to recognize the difference between different types of chemical compounds based upon the elements that are involved. Now we're going to take another step forward.
Ooh, there's that big bad word from last unit. Electronegativity. I know that was everybody's favorite word.
We're going to use the electronegativity of the elements to decide if a compound or a bond would be ionic, polar, or covalent.
Sure. We got to classify these things. So I'm basically just going to find the electronegativity difference, which is subtract the 2. So we got to look them up in table S.
Yep, they're all listed back here. Electronegativity, it's a number between 0 and 4. Right there, boom.
Yep, right there.
Less.
I'm going to take those two numbers and I'm going to subtract them. If the number is 1.7 or greater, it's ionic.
Right.
If it's 0.5 to 1.6, it's what we call polar covalent, which is sharing but not evenly.
I missed everything.
We're sharing but not evenly.
Right.
And then if we're below 0.4, we are nonpolar covalent. We are sharing evenly.
Right.
Okay. That's the way to sum it up. And you're going to see that the polar bears and the penguins and the pogo are doing this.
Because we got to take into account the fact that different elements have different pull for electrons. Right?
Yeah.
So if
some are thirstier than
you
others.
have a thirstier pull for electrons and I have some to share, you're going to share them unequally.
Right.
The idea that if we combine a metal and a nonmetal to get an ionic compound, or two nonmetals to get a covalent compound, still trumps all. It's just that in this nonmetal combination, there's another sub-level. It's either nonpolar or polar.
Really, and that is the truth. And I put this disclaimer in there because there's always one or two that sneaks into the practice that defies that rule. We want to call it a polar covalent, but when we look at it, it's a metal and a non-metal, and it really is ionic. So just to cover what you're going to call it.
Basic definition again, what an ionic bond really truly is. It's an electrostatic force of attraction between oppositely charged ions. One metal ion and one non-metal ion, because that's how you get the opposite charge. Metals are positive, non-metals are negative. So metal plus non-metal ionic bonds, you don't even have to worry about electronegativity difference, really.
And just, cation formation, and form that positive ion, the electron is going to be completely transferred from the metal, creating the positive, and it goes to where again?
The anion, the non-metal,
there you go.
Where the electron is completely transferred to the non-metal, making a negative ion. So again, positive and negative transfer electrons, get stuck in that electrostatic force of attraction we call a ionic bond.
That's really how it works.
Polar bond, on the other hand, and molecules, because your bond within a molecule could be polar or non-polar.
Correct.
And then the molecule itself could be polar or non-polar. So there's two layers.
So let's do just the bond first. A polar covalent bond is where they are shared unevenly between two atoms, creating a polar bond within the molecule.
Right.
So that makes sense?
Two atoms connected, but one's pulling the electrons more than the other.
So now
we're still connected. We both have octets, but
we're sharing.
He doesn't like to share so well. I got to force him to share a little bit. Within a molecule, the electrons are shared unevenly around the entire molecule. Uneven distribution of charge.
So we're going to learn to cut the molecules in half this way and then in half this way and compare sides.
Visually looking at geometry. Correct. Okay. Now, bond formation in nonpolar covalent molecules. So nonpolar is when the electrons, two hydrogen atoms, they're both equal strength. He might be pulling, but I'm pulling back the same exact strength.
And so now we're sharing perfectly evenly.
It's not a polar bond. No poles either end. Neither one of them gets the electrons more than the other. So it's a nonpolar bond.
And our END would be 0. Right? Perfectly nonpolar.
Technically, according to the rules, less than 0.4.
Now, with a molecule, though, this is the summation of all the bonds like vectors, but now it's symmetrical. So if there's a pull in the down direction and a pull in the up direction, they cancel each other out and same side to side. And if they cancel each other out all the way around, it's the same on all sides. There is no positive side or negative side. The trick is that the bonds within could still be polar. But if the polar down cancels out with the polar up, then
the overall molecule
not
is
polar.
neutral, right?
There you go.
Okay.
So
it's like a three-way fuel. This lecture is difficult to understand without a lot of visuals looking at molecules. What we want you to remember was on the first slide about the electronegativity differences, ENDs, okay? And figuring out polar versus nonpolar within the molecule itself. We got a couple minutes, so we'll show you. First of all, Mr. Noakes has drawn a couple different molecules. Looking at these molecules, we will determine if the bonds are polar or nonpolar.
Okay, so and this is a good time to talk about this because we're only gonna do one H and one C, like right here. We're only gonna do that. We're not gonna do 4 H's. Okay,
You got to take a call, Milks. You got to take.
I got you. Can I have the paper though? I got you. So I look up hydrogen's electronegativity, and I see it's 2.2. And I look up carbon's electronegativity, and I see it's 2.6. So 2.6 minus 2.2 is 0.4. So that is a non-polar bond. Are we okay with that? Okay. Now, if one of them's a non-polar bond, they're all going to be non-polar bonds. And next we have to do the whole test of the molecule itself. So I know you can't see me, but I'm going to go to the board. I'm going to cut the molecule up and down. Is it the same on both sides? I'm going to say yes. And then if I cut it horizontally, is it the same top and bottom? And I'm going to say yes. So this whole thing is symmetrical, making this a non-polar molecule.
Mm-hmm. He right. Now the next one, H, I think you wanted to do Cl there. So squeeze a little L. Okay. HCl. If you look at the difference in polarity.
Minus 2.2.
Look at him. He's got it memorized.
Well, some of them we've done quite enough.
1.2.
2. So
this would be in the polar
covalent
covalent range, meaning the bond between the hydrogen and the chlorine. One of them, too, is going to pull them more dominantly than the other. It's the chlorine in this case. So he's going to draw a little symbol.
When I cut it this way, is it the same top and bottom?
It is.
Now, when I cut it this way, is it the same top and bottom?
Left and right.
Left and right.
No, it is not.
No. So now this is a polar
molecule. And I want to squeeze a symbol in there.
Go ahead. Oh, I can do the partials. Oh, there you go.
That little symbol I drew in green
tells me
shows you which element is hogging the electrons in this polar bond.
Right, and if you look at this part,
it's got a little plus sign.
It's got a little plus sign.
Yeah.
Okay.
Yep.
All right. N and H. I need help with N. I don't remember.
Nitrogen's polarity 3.0. The electronegativity 3.0
minus 2.2
0.8. So these are going to be in the polar covalent range for the bond. So every hydrogen-nitrogen bond is a polar covalent bond. And nitrogen is going to win the push-me-pull-you of that polarity.
And we'll learn that I've learned that whenever there's a lone pair, the molecule is going to end up being polar.
Right.
We'll show you why when I do the actual
Vectors.
cutting cut. Let me go up and down first this time just so I can see left and right. It's the same.
Left and right side of that molecule are the same.
But
top and bottom
is not.
Are not.
So now this is a polar molecule.
Yep. And I hope you're wondering, that polarity, that symmetry that I studied in geometry and all that stuff, why was the point? What was the point in knowing that? Well, chemistry was the point in knowing that.
And here's the classic.
Carbon double bond 0. Yeah. Oh, so this is a carbon dioxide molecule that we are drawing in from memory what the shape of the molecule looks like. And we're going to tell you straight up, oxygen is more electronegative than carbon. It's, let's see, oxygen is 3.4 and carbon is 2.6. So if you do the 0.8 would be the polarity of the bond. So
this is a polar
covalent. And
bond.
Meaning that the oxygen wins the push me pull. You can put those little signs in there. You go ahead. He's gonna draw that. Yep. Bloop. Little arrow. Bloop. Pushing in opposite directions.
So if I drew these right, the arrows would be the same length.
Yep.
And when I cut it this way,
symmetrical.
Same on both sides. When I cut it this way,
symmetrical.
This is a non-polar molecule with polar bonds.
So it is important to know this stuff because you might be hit with that question. Which are the bonds in this molecule polar or non-polar?
This is the classic question with CO2. Why is it polar bonds but a non-polar molecule? Because it is symmetrical in shape.
And there's a ton of practice in the packet and the POGL to really get this happening and ask us to pull out the model kits if you really need to.
Yeah, seriously.
See ya.